Artificial intelligence is consuming computing power at a rate that traditional chip scaling can no longer sustain. Right now, global AI compute demand is doubling every 7 months, putting immense pressure on the physical limits of our hardware. For decades, the tech industry handled increased demand with a reliable formula known as Moore's Law. We simply shrank the transistors and packed more of them onto standard, flat, two-dimensional silicon wafers, creating ever-denser systems on chips. But the industry is hitting a wall. The transistor density and data bandwidth required for modern AI have grown so massive that a single, flat silicon chip can no longer physically route the information fast enough to meet demand. The method of solving computational bottlenecks by simply squeezing more components onto a flat plane is reaching its absolute limit. On a standard silicon wafer, we hit a hard boundary. Lithography tools have a maximum reticle size of 858 square millimeters. Printing chips larger than this bounding box introduces inevitable flaws, leading to defective chips and unviable production yields. Beyond the physics, there are geopolitical borders. Manufacturing traditional chips smaller than 5 nanometers requires extreme ultraviolet lithography machines, like the one pictured here. Because of international trade restrictions, access to these specific tools is strictly limited for certain nations. With physical limits capping the maximum size of a chip and trade policies restricting who can buy the machines to make them smaller, the global semiconductor industry is searching for entirely new architectures to keep advancing. One major engineering bypass is a shift in geometry. Instead of trying to scale down on a flat plane, engineers are scaling out, moving away from 2D limitations and building up into 3-dimensional vertical space. As we can see in the floor plan on the left side of this diagram, a massive monolithic processor is intentionally broken apart. The system is divided into smaller, specialized modules called chipsets, separating the logic, memory, and power systems. Looking at the right side of the graphic, those separated chiplets are then reintegrated into what's known as an advanced package. By stacking these dies vertically, manufacturers bypass the printing size limit while increasing processing speed because the physical distance between components is shorter. These 3D configurations are already out of the lab and actively powering the next generation of server-class CPUs and AI accelerators. Because manufacturing a single, massive chip at a 2-nanometer scale is prohibitively expensive, splitting the architecture into a 3D package is what makes these high-performance compute nodes financially possible. But if traditional silicon is hitting a wall, what happens if the industry abandons silicon entirely? We can see one answer in this newspaper clipping. Researchers at Fudan University recently developed an integrated 2-dimensional semiconductor microprocessor, a major engineering step away from traditional silicon-based designs. By utilizing atomically thin 2D materials, like the ones displayed in this exhibition photo, nations can target 5-nanometer performance without needing access to the specific EUV lithography machines currently being restricted. Software developers are adapting in parallel. Companies are heavily optimizing their algorithms, refining training and inference methods to extract maximum AI performance out of whatever hardware they have available. By combining alternative materials with smarter software, developers are finding ways to advance without the specific tools that were once considered essential for high-end computing. The strategy of simply printing smaller and smaller transistors on a single flat piece of silicon has reached its functional end. Going forward, high-performance computing and AI will rely on a mix of technologies: vertical 3D chiplet stacks, silicon photonics to transmit data via light, and brand new 2D materials. Physical laws and trade policies have effectively broken the industry's reliance on a single path of advancement. Computing is now evolving into 3 dimensions, defined as much by spatial stacking as it is by the materials used.